discussion of basic ideas that will hopefully not take more than 20 minutes or so, and then we move on to the very topic of these lectures, namely what happens to the phase transitions that we have started discussing if they happen in a visible system. But before I continue our discussion, let me just briefly show you these pictures that illustrate what we talked about yesterday, namely critical evanescence close to critical point. So these are pictures of actual experiment that shows this critical evanescence for a mixing critical point. So it's not a liquid gas critical point, but it's a mixing critical point, and the big advantage is that you can do this on your kitchen table. You don't need high temperatures or pressures. And so you start with two fluids, in this case hexane and methanol, that are miscible at high enough temperatures. So that's this picture here. So you get one uniform clear fluid. But there is a critical temperature below which they don't mix anymore, which for this mixture is roughly 36 Celsius. And therefore, if you go below that, it's a lower picture, you actually see the two phases appear. Right? You have two phases of two liquids, and they don't mix anymore. Right? And in between, close to this critical temperature of about 36 Celsius, you see exactly what we discussed yesterday. The fluid becomes milky because you have large fluctuations of relative densities, or let's say the relative concentrations between these, and this indicates a divergent correlation. Okay, so just a side remark. Now back to our main topic. We have discussed basic ideas of phase transitions, and as you've probably noticed, I've mostly talked about phase transitions that are tuned by temperature, or at least occur at non-zero temperatures. These are nowadays known as classical phase transitions. And as, of course, I'm sure all of you know, there's a different kind of phase transitions that occur at zero temperature. In a quantum system at zero temperature, if you tune something else, if you tune magnetic field or pressure or chemical composition or something of that type, this is a class of quantum phase transitions. And what we are going to do in the next 20 minutes or so is we are going to see how the concepts which we developed yesterday, how they have to be applied or generalized to the case of quantum phase transitions. So this would be 1b in my counting quantum phase transitions. So as we already said, so these are transitions that happen at the absolute zero of temperature. And the tuning parameter is some non-thermal parameter, right? So as I said, pressure or magnetic field or chemical composition in an alloy disorder, as you will see, or some other non-thermal parameter. Okay. So let's look at an example. So that's the example that many of you have already seen. So this is another phase diagram. That's a magnetic phase diagram. It shows the magnetic properties of lithium holmium fluoride as a function of temperature and the magnetic field. Okay, so let's first forget about the magnetic field and let's look at the temperature axis, right? So then what you see is you have a material that is ferromagnetic at low temperatures and paramagnetic at high temperatures. Now this by itself, of course, is not very interesting or surprising. That's the same thing as many ferromagnetic materials do. What's maybe interesting is that the Curie point is extremely low, right? It's not 1,000 degrees like iron. It's only about 1.5 Kelvin. And I don't want to get into the question of why this is so. But what it of course allows you is to actually manipulate this magnet by other parameters. Right? Iron is a very robust magnet. It's very hard to destroy the magnetism. This is a much weaker magnet, right? You don't need much thermal fluctuations to destroy it. Therefore, you can actually do something to it by applying a magnetic field. Now, to understand what's going on here, you need to know a little bit about the crystal structure of this material. So that's not cubic. It has an anisotropic crystal structure with an elongated unit cell, which realizes uniaxial symmetry, meaning that the spins, which live on the holmium atoms in this material, so they like to be either pointing up or down, but they don't like to be in the plane, right? So this realizes an Ising magnet. And the magnetic field that the experimentalist used here is actually perpendicular to that direction. So it's not a longitudinal field, like the one that you write down in your StatMag class, if you do the simple Ising model. It's a transverse field. And this will become important in a second. Okay, so now let's look at this. So this axis is easy, and we can understand it from what we did yesterday. Now let's talk about this axis. So what you see is, if you crank up the magnetic field, then the ferromagnetic transition gets suppressed, and there is a critical field at about 5 Tesla or so, beyond which the ferromagnetic order vanishes altogether, right? So then here you have an example of a quantum phase transition, right? It's a phase transition between two ground states, a ferromagnetic ground state and a paramagnetic ground state, t equals 0, and it's tuned by this transverse magnetic field. Okay? So how does it happen? Why do we get this transition?
Quantum fluctuation.
Quantum fluctuations, yes. So that's an important keyword here. It's clear that something must replace the thermal fluctuations in a normal phase transition, right? So the normal phase transition, what really destroys the long-range order, let's say the ice crystal, is solar motion, right? But we don't have that here. So the only other thing that we can think of, at least I can think of, is quantum fluctuations. And it turns out that in this case, we can actually see this at work by writing down a very simple toy model, right? So let's make a toy model, and let me emphasize toy. So I'm not trying to model the microscopic physics of this material, which has some interesting caveats. We're trying to make a toy model to understand this transition, okay? So what ingredients do we need? We need some interactions, right? To produce a ferromagnetism in the first place. So we could write down a classical Ising model. So let's make a toy model. And one part of the Hamiltonian has to be something like a classical Ising model. So let me just write something down, minus j, sum over ij, that's nearest neighbors. And then we need an interaction between Si and Sj, spins on the nearest neighbor sides of the lattice. And remember, I said uniaxial symmetry, so we need one component. Let's call this component the Z component, right? That's the one, that's the preferred direction. Okay. And as I said, that's a toy model, right? The nearest neighbor condition is not fulfilled in this material, and there's many other caveats, but it's good enough to discuss the transition. Right, so with this model, we can discuss this axis, right? But we have no magnetic field yet. So what should I add to add the transverse magnetic field?
PSX.
Something like that, right? And I've absorbed all the constants, Bohr magneton and things like this in the definition of what B is. So that's my toy model, and it turns out it's good enough to understand the transition. And the easiest way to actually see the quantum fluctuations at work is to remember that you can decompose the x component of the spin operator in the as plus and as minus, right? So as x is something like as plus as minus, and that is a half or not a half, depending whether you use Pauli matrices or the actual spins. And now you see what this term is doing, right? You really see at the microscopic level that this is competing with the long-range interaction, right? This term likes the spins to be parallel, right? Whereas this term likes to flip the spins up and down. And therefore, if this field gets strong enough, you destroy the long-range order, right? And so this gives a microscopic toy example for how a quantum phase transition works. It's a quantum zero-point motion, or the quantum fluctuations, or whatever language you want to use, that takes the place of the thermal fluctuations in destroying the long-range order. And of course, there are many more examples, right? There's transitions in ultra-cold atomic gases, mod transitions, for instance, metal incidental transitions. other magnetic transitions in other materials, like in metals, but the basic idea is always the same. You have a transition between two ground states, and it's driven by quantum fluctuations. All right, so now the question that I posed is, can we actually generalize the ideas that we developed yesterday in the case of quantum phase transitions? So this would be ideas like scaling and exponents and things like this. So that's the goal now. Generalize phase transition concepts to quantum phase transitions. And let me introduce a very important idea right away, an idea I will use extensively when later on when we discuss this order, and that's the idea of the so-called quantum to classical mapping. Okay, so in order to understand how this quantum to classical mapping works, let's first look at the partition function of a classical system. Okay, of course you know how to do this. Partition function of a classical system is, in general terms, given by a phase space integral, right? So we have some. So let me see how much detail I want to write. So you have some integral dp dq. And this could, it is in general a high dimensional phase space, of course. And then we have e to the minus beta is a classical Hamiltonian function, right? That's a general expression for a classical partition function. And the interesting thing about this in many cases you can factorize this partition function into a term that depends only on coordinates and another one that depends only on momentum. And it works whenever the Hamiltonian falls apart into a kinetic energy and a potential energy that depend only on momentum on one side, coordinate on the other side. So if that happens, then this of course becomes dp e to the minus beta kinetic energy, it's a kinetic piece, times integral dq e to the minus beta potential energy. Right? And of course, this is all symbolic notation. This is all high dimensional in general. Okay, so what does it buy us? Well, there's one more step. You just need to remember that, again, in generic classical systems, in very many classicals at least, the kinetic energy is simply quadratic. Right? It's something of the structure of p squared over 2m, or maybe modulus p, or some other simple term. Right? So in that case, you get something like a Gaussian integral here, right? And of course, as you all know, Gaussian integrals can never be singular, right? The Gaussian integral, you can carry it out if you want to. You guys get some analytic function. So the upshot of this is that in very many cases, generically, there will be no singularities in the partition functions that arise from this piece. Okay? But as we defined the phase transition yesterday as being a singularity in the free energy, meaning also, of course, a singularity in the partition function, that means all the phase transition physics has to come from the configurational part, right? And therefore, and that's now a crucial step, if you're only interested in phase transition physics, in universal behavior, critical exponents, things like that, just forget about this, right? It will never produce any singularities. It will produce some non-singular, smoothly varying function close to the phase transition point, which of course is important if you, let's say, want to know the precise value of Tc for a material, but it's not important if you're only interested in the singularities, the critical exponents. Right? So therefore, for our purposes, this is as good as simply writing beta minus beta v of t. And again, emphasize that this is only true if you are interested in the singular behavior of the free energy and not in precise numbers for a particular material, right? So the singularities arise from the configuration part only. So why is this interesting? Well, this explains, I would argue, why you can use these extremely simplified toy models just like the classical Ising model and still get the correct critical behavior of a complicated magnetic system, right? Clearly, a real magnetic degree of freedom is not a simple plus minus 1 degree of freedom, and certainly that is not completely static. And so from a more general point of view, the reason why this works, right, is because you just need the configuration part, right? You don't need the dynamics. As long as you're interested in partition function, right? Okay, another way of saying the same thing is to say that for a classical system, the static behavior, which governs the thermodynamics, and the dynamics, the real-time dynamics, which is of course influenced by this, they decouple, right? And what you do is, if you are interested in phase transition physics, you first solve the static problem, for instance, using a trivial classical Ising model, and then later on, if you want to, you can add the dynamics and see what it does, right? So classically, the two decouple. Okay, so now let's try to do the same thing for a quantum phase transition. Let's look at this one, right? So we can do the same thing. We start from a partition function, right? So maybe mapping, so that's the classical case here. Let's look at the quantum case. So partition function, as you all know, of course, is the trace of e to the minus beta h. And let me put the hat here to emphasize it's our operators now. Okay, which is of course the trace of e to the minus beta t plus v. Okay. So now, can I continue along the same lines now? So what I would like to do maybe is to write this as e to the minus beta t times e to the minus beta v, right? Following the same idea that we used here. Why can't I do that?
Yeah, no, community.
Right, the two don't commute, right? So therefore, the factorization doesn't work. So what this immediately tells us is that in the quantum case, static and dynamics are not decoupled. And therefore, if you're interested in a quantum phase transition, you cannot first just solve for the statics and then add the dynamics later on. You have to solve for the statics and dynamics together, right? Okay, so I cannot factorize, but I can do something that's almost as good. Namely, I can factorize under the total decomposition. Right? While e to the t plus v is not the same as e to the t times e to the v, right? That's because they don't commute. E to the t plus v is the same as a limit n to infinity e to the t over n times e to the v over n to the power of n. And that's a general operator identity, right? So it applies to any operators t and b, not just to kinetic and potential energy. But we can now use it to actually decompose our partition function, right? And incidentally, of course, this is the same trick that you can use to construct Feynman's path integral in quantum mechanics, right? So what that does for you is that it effectively slices the inverse temperature factor beta, right, into many, many slices. So we get many imaginary time slices, which means we effectively get one more dimension in our problem, right? In addition to space, which is coded somewhere here, right, we now, in our partition function, have another coordinate that counts which of these factors we are considering, right? And if you have constructed the Feynman path integral, which most of you probably do, you know how it works, so you integrate, you write it down, you insert operator identities. So I'm not going through the mechanical steps. The upshot is, if you do all of that, then you arrive at a representation of the partition function that looks just like a Feynman path integral, with the difference being that instead of having an IT, we now have a beta. So we have an imaginary time instead of a real time. Okay? So this leads to an imaginary time, or some people call this Euclidean. Path integral for the partition function. So z is then given as integral d q of tau, and there's an e to the minus, so let me see how I want to write it down. S of q and tau. And so if you go through the steps, then you get the partition function as a path integral, and here you get a real exponent, a real action, right? No IT.
Question.
Yeah?
Formally, Hamiltonian is defined as P times Q dot minus H. So there is this surface term, which in general drops out. But it's not trivial to me how it drops out in the quantum case, because there's a time derivative there.
Yeah, but see, you have periodic boundary conditions on that interval from 0 to beta. And because the periodic boundary conditions, all the boundary terms that you may be thinking of, sure, they drop out, right?
Oh,
yeah. It's different if you can get the Feynman propagator, because they have two separate times, right? But here this wraps around. There's periodic or anti-periodic boundary conditions, depending on what kind of particles you think of.
So it does just for general information, does it give you some topological terms?
I come to that. Yes, that's a very good point. Let me go forward a little, okay? That answer your question. Okay, so we get this type of formulation, and that forms the basis of the so-called quantum to classical mapping. Because in many cases, you can now go ahead and actually interpret what you have here as the free energy of a classical system with d plus 1 dimensions, right? The time simply acts as an additional dimension. So that's the idea. Whenever you can do that, whenever you can interpret what you have here as the Boltzmann factor of some hypothetical classical system, then you can have achieved the mapping between the quantum partition function in d dimensions to a classical partition function in d plus 1 dimensions, right? And whenever this works, it's extremely useful because we know a lot about classical systems and we can use all of this knowledge to understand the quantum problem. Okay, so let's write it down. Means I have a quantum phase transition. Imaginary time acts as extra dimension. And if we are somewhat sloppy and don't think about the caveats, which I will be talking about in a second, we can say that the quantum phase transition in d dimensions is equivalent to a classical transition in d plus 1 dimensions. Okay, and so whenever that really works, that's extremely useful because we can use a lot of intuition from classical systems. But there's a number of caveats that need to be pointed out. The first, maybe most important one is this only works for thermodynamics because it's based on decomposing the partition function. So as long as I'm doing thermodynamics, then I may be able to rely on that. If I want to do something else, like real-time dynamics, right? So if I want to calculate dynamic correlation functions, let's say maybe productivity or something like that, then you cannot rely on the mapping. Then, at least not in general, and you need to go back and actually redo your quantum theory from the outset, right? Works for thermodynamics only. And that's because it's based on decomposing Z. The second caveat, maybe less critical, is that I emphasize that we may be using our intuition from classical physics to use this, but of course, very often the resulting classical system, while classical, will be very unusual, right? There's no guarantee that the way this new dimension enters resembles in any way what we know about well-known classical systems. Right? So you may get a very unusual classical system, and then your intuition may not be worth much. But then again, it may. It depends on the case-by-case basis. So the classical system that you get may be usual, and in particular, there's no reason for this new dimension, which represents imaginary time in the quantum problem, to enter in any way similar to the real space dimensions. So therefore, in general, you will get an anisotropic system, right? And we will actually see this at work later today when we talk about this order. Okay, and another very important caveat that touches upon what you said is, of course, all of this assumes that this action that you get after you go through the steps of deriving the path integral is actually real, right? And there's no guarantee. As we know, quantum mechanics is not real, right? So therefore, depending on the system you're looking at, you may get a real action here, then you're in good shape. Then you can interpret this as a classical free energy, classical Boltzmann factor, and then the mapping works. Or alternatively, you may get something that contains phases, right? And then this exponential is not even positive definite, right? If there's a phase term here, it could be negative. And then it's clear you cannot interpret this object as a classical Boltzmann factor. and then the mapping just doesn't work, right? And what case you get depends A, on the system you have, and B, on how clever you are in actually carrying this out, right? Very often there's more than one way of representing the partition function, depending on what basis states you use for your functional integral construction, coherent states, or maybe simple position and momentum states, or something like that. And depending on what you use, you may or may not get a real versus an imaginary complex representation. In any case, whenever you get a real one, then you're in good shape and the mapping works. If you do get a complex representation, then you have what the numerical people, the computer simulation people, call a sign problem, right? Because then you cannot interpret this as a classical weight, a classical probability, and then for the numerical people, the Monte Carlo doesn't work. Or in general, in our case, we cannot map it to the classical system, right? So only works if the action S that we get is real, so that we can interpret it as a classical free energy. If we get phase terms like Barry phases or something like this, right, then it does not work. So let me write that sign problem as a keyword here. And one example for which it does work very easily, actually, is this toy model that we looked at 10 minutes ago. Give me a second. 10 minutes ago, the transverse field Ising model that we wrote down as a toy model for our lithium chromium fluoride magnet. There you can actually do the mapping, and you indeed get a classical free energy, or something that can be interpreted as a classical free energy. And it turns out this is equivalent to simply an Ising model in one higher dimension. So there it works beautifully in the most trivial version. You map the transverse field Ising model in d dimensions onto a classical one in d plus 1 dimensions. Okay, you had a question?
Yeah. When you map to a classical system, you sort of have to imagine that temperature has been absorbed into all these things, right?
Say it again?
When you map to a classical system, you have to imagine that temperature has been absorbed into all your units of energy.
Absolutely, yes.
Is there anything tricky about that? Or?
Not really, at least not if you're essentially only interested in universal properties, right? So, of course, you can do this mapping such that the partition function is really a phase-field representation of the quantum partition function, number by number, not just structurally. But then you need to keep track of all of those, right? You need to keep track of the width of your time interval and take the limits seriously and things like that. If you're only interested in universal behavior, none of this matters, right?
What do you do with fermionic packing or fermionic gas numbers?
Yeah, well, in general, for this type of problem, it doesn't work from the very outset because of that reason, right? Because it's always a side problem.
Is this then why you get a ferromagnet in the 1D Ising chain, because it maps onto the because it maps the classical 2D problem, and therefore you can get order?
Yes, yeah. So at zero temperature, with this model that we wrote down, you can get order in one dimension. Yes, that's true.
So I'm always amazed by the correspondence between such a classical system and a quantum system. So could you please comment on whether there are deep physical reasons behind this?
Okay, I'm not sure what you want to call a deep physical reason. I think probably not, right? And the reason why not is exactly, you can see this from the fact that it doesn't always work, right? If there was a deep relation that relates quantum mechanics in general to classical physics, right, then something like this should always work, right? So I see it mostly as a technical observation, a technical trick, right? I may be wrong. Okay, so now once we have this, so let's just take it, let's run with it, let's see how far it takes us, right? So let's, for the moment, assume it works, right? And let's see what we can get out of that. One very useful insight is how to generalize scaling to the quantum case. Okay, so we wrote down William's scaling hypothesis for the free energy last time. And the question is, what do we do if we have a quantum system? So remember what we wrote down yesterday. So we had the free energy is a function of two variables, the distance from criticality, little t, and the magnetic field P. And we said that's d to the minus d times f of the rescaled variables like that, right? Now, well, we just said the quantum phase transition in d dimensions is equivalent to classical one in d plus 1 dimension. So what this suggests is that we should simply replace d here by a higher dimension, right? So we should write f of t and b is b to the minus d plus, now what should I write here? If space and time really enter the theory symmetrically, as happens sometimes, but not always, I should simply write d plus 1, right? And that's the case for our toy model. In general, space and time will enter asymmetrically, so it will not be d plus 1, but d plus something, and we know what that something is from yesterday, right? We need the exponent that relates the length and time scales. Because one time dimension will count not as one space dimension, but as z space dimensions, right? So it should be d plus z here, and otherwise it's the same thing, right? That's a simple generalization of scaling. One needs to be careful here. T, of course, now is the distance from the critical point along the quantum tuning parameter axis, right? It's all at 0 temperature now. Right, so this is distance from the quantum critical point. It has nothing to do with temperature. Right? And we can go one step further, and that's particularly useful for experiments, because clearly experiments are not done at 0 temperature, right? So therefore, we need somehow to bring the temperature in the game if you want to make a prediction that somebody can actually measure in the lab. And so I want to add the temperature as an extra parameter to my free energy, right? And certainly do this. I now want to look at the free energy, for instance, of our lithium holmium system as a function of the distance from criticality, which in this case, in our toy model, would be b minus bc over bc, right? It's measured along the quantum direction, not along the temperature direction. Then the longitudinal field, the transverse field here. And then we have the temperature added as an explicit parameter. And of course nothing changes here. But what we need to know is how we will have to scale the temperature in the second step of our scale transformation, right? And I think you asked me about this yesterday, right? And I said, let's wait until we talk about quantum phase transitions. So the crucial insight is that the temperature is an energy, right? But an energy is an inverse time. And so therefore we know how t has to scale because we know how times scale, right? Time scale like length to the z. And so it's clear we have to have a b to the z, right? So this, if you want, is a straightforward generalization of Beadham's scaling hypothesis to a quantum phase transition, where I've included the temperature as an independent parameter that can tune away from the critical point.
Sorry, but quantum phase transition happens at t equals 0, right?
The quantum phase itself is right at t equals 0, right? And I now have two independent parameters that I can use to tune away from the precise critical point. And for the classical transition, for instance, the critical point of our mixture in the beginning, I have one parameter. I can tune t, and this takes me away. Here I have two different parameters, right? I can either tune the transverse field a little away from the critical value. That's this parameter here, right? Or I can actually raise the temperature that also takes me away from the critical point. So I have two independent parameters. One is the temperature, and the other one is a quantum tuning parameter. That could be transverse field in our toy example, it could be pressure or whatever else you're using. So I have two parameters that can tune away from the quantum critical point. And of course they come with different scaling behavior. Okay, any questions about any of this?
Sorry, maybe I'm just getting a little confused about the difference between your transverse field and what you call
Yeah, I'm sorry about this, but so this little t is the distance from the quantum tuning parameter of the quantum tuning parameter from its critical value. Right? In our toy model, we were tuning the transition with a transverse magnetic field. Right? But of course, the B field that showed up yesterday for the first time is a longitudinal field that couples longitudinal to the order parameter, right? So in our toy model, this would correspond to adding a second field in the preferred direction of the spin. So in that problem, there are two different magnetic fields. One acts as what we could call the conjugate field to the order parameter. That's a longitudinal field. That's this one. It plays the same role as a field in the classical Ising model. And the other one, the transverse field, doesn't really play the role of a field here, right? It happens to be the tuning parameter with which you tune the transition. And if for a different material, it could be pressure or chemical composition or something like that.
So do we need to keep this other B at all? I mean, can we just throw it out?
Well, you need this other B if you want to be able to tune through the transition at zero temperature. Or you mean this B?
Yeah, that B.
Well, strictly it depends on the experiment, right?
Okay.
If you don't apply a longitudinal field, then you don't need it. Question?
How do you know that the exponent for the quantum t is the same as the classical?
I've not talked about values, right? I don't know what number that is.
I mean the t, you have one over mu.
Little t.
Small t. Yeah, that.
Well, small t is just an abbreviation, maybe I'm misunderstanding. It's just an abbreviation for the relative distance from the quantum critical point.
Yeah, but you have exponent 1 over mu, right? Is it the same mu as in the classical?
Yeah, and the value of mu may be different, right?
Okay.
It doesn't have to be the same value, right? There will be some mu for this transition that potentially, and as you will see, is different than the mu for the classical transition. Right, so if there's no further questions, then we are finally at the end of the review and can move on to the main question. So what happens if you add this order to either a classical or a quantum phase transition of the types we have discussed? Okay? So number 2. phase transitions and disorder. And let's start to talk a little bit about what I mean if I say disorder. So if you say, somebody saying he or she works on disordered systems, what do you imagine?
Potential disorder.
Potential disorder, so you are a theorist. Somebody? The experiment, where could disorder come from?
Structure factor.
Could be impurity atoms, right?
Discriminations.
Yeah, so longer extended defects, right? And there could be grain boundaries or something like this. So there's lots of microscopic reasons that could produce disorder, right? Fundamentally, what you probably have is you can have dilution, you can have vacancies in your crystal, right? Vacancies or impurity atoms. Or you could have extended objects like dislocations. Or grain boundaries. So there are many microscopic reasons, and it's just a partial list of course, there are many microscopic reasons why there would be some randomness, some disorder in your system. And there's one important distinction to be made right away, before we start talking about modeling this in a theoretical way. This has to do with timescales. So if you're an experimentalist, there's a very important distinction to be made between your lab timescales and the timescales on which these guys move, right? And this leads us to very different types of theories in the end. So the one case is the case where these objects, whatever they are rather mobile, right? And they move on timescales that are shorter than your lab scales, right? Maybe let's even look at the ideal case, and let's assume they are fully in equilibrium over the timescales, right? So then you get what's called a Néel disorder. So this all fluctuates on timescales that are much shorter than the timescale of your experiment. And again, in the ideal case, let's assume that they may have enough time to fully equilibrate, right? So if that's the case, then what would you do? How would you theoretically treat them? If they fully equilibrate over the timescales you're interested in.
Dynamical variables.
Exactly. There's nothing special about them, right? They play the same role as any other dynamic variable, as a spin variable in the magnet or the position variable in the liquid. If they are fully in equilibrium, they are just included in the partition function, right? So in that sense, there's not really much new, right? At least in this extreme limit, when they fully equilibrate, the distinction between what we call disorder and what we call dynamic variables is artificial, right? They all behave the same way. They all fluctuate in equilibrium over the incremental scales, and therefore they can all be treated in the same way. So we don't need any new methods, and strictly we don't expect any qualitatively new physics, right? So that's a simple case. Another way to think about this is that you average the partition function over these variables. Right? If you include them as dynamical variables in the partition function, they just become another integral or sum outside of the Boltzmann factor. So one way to think about this is to say that you average z in this case, right?
I mean, in this case can be quite complicated. Like it's just another new degree of freedom.
Sure,
which is
yes,
interacting
yeah.
with you.
But conceptually, my point is that conceptually it's not different from just including more dynamical variables without calling them disorder, right? Sure, if they are complicated enough, then you just get a system with many, many more degrees of freedom, and that, of course, can pose an additional complication. So that's, as I said, conceptually at least the easier case, and we're not going to talk about this at all, right? I want to look at the other case. I want to look at the case when these guys are so slow that they essentially don't move over your lifetime scales, right? And that's, of course, what normally happens if you think about, let's say, a crystal with a vacancy, right? As long as you don't heat it up, the vacancy will just be sitting there. And so the other case is called quench disorder, and that's when the inequality is the other way around. So the disorder is frozen. Does not change over the time scale of your experiment. And if you think about it for a second, it's clear that this is conceptually much harder, right? Because what that means is that what you need to do is you need to calculate whatever you're interested in, the observables, for a particular disorder configuration, one sample, right, with a particular arrangement of the vacancies, and then maybe another one, and each one will have its own observables. So therefore, if you're interested in averages, what you average is not z, but what you need to average is a logarithm of the partition function, because you want to average the free energy. This gives you the observables. So let's assume you are interested in thermodynamics for the moment. So what you average in this case is not z, because you don't move, but what you average is the free energy, and that's log z, right? So what you need to do is you need to average the free energy, which is the same as averaging log z over the disorder. And the log is a nasty function, so averaging log z is hard, whereas averaging z itself is easy. And people have devised tricks to actually circumvent this problem. The most famous is the replica trick that some of you, or many of you, may know. Here the basic idea is to just rewrite the log, right? So you write log z as limit of little n to 0, z to the n minus 1 over n. And if you now carry out the average, you have to average z to the n, which is much easier than averaging log z. And if you want, you can interpret z to the n as n powers of z, which means the partition function of n identical systems, n replica, that's as the name comes from, right? And this is a useful technique which sometimes works and sometimes doesn't. And there's actually explicit counterexamples where people have proven that it gives a wrong result. If it works, it's great because you can actually do this, carry out the disorder average first, and then get a system that effectively looks clean, and you can apply all the techniques for clean systems to that. But often, as I said, it doesn't work, and therefore I will not use this method at all, right? I just mention it because it's used in many contexts, and it's very useful in some cases, and not at all useful in others, right?
Can you maybe clarify what you mean by it doesn't work? Are you meaning that there is no regular symmetric tracing or something else?
No, I mean something else. I mean that even with the most sophisticated evaluation of the resulting class translation invariant theory, you get results that are manifestly wrong. I think Sombauer has written a few papers about counterexamples to that, and I can dig out the references if you're interested. No, sometimes you actually need sophisticated techniques, and if you use those, you still get the right result. This is still okay, right? But sometimes you simply get nonsense. And in particular, maybe more along the lines of what you said, much of the physics we were discussing in the last two lectures will be of the type that's very hard, I'm not saying impossible, but very, very hard to get it within a replica technique. So all the physics that is based on rare regions and non-perturbative physics, there are very few results that this can be reproduced by using this.
Question?
Yeah.
So I think you're thinking about phase transition is about the non-analytic behavior in something, and then the replica trait, obviously there's analytic continuation. Then you're looking for something non-analytic using analytic continuations. So my question is, why does it work?
Yeah, of course, you're exactly right. Let me rephrase what you say, right? The question is whether we can actually commute this n equals 0 limit with all the other operations that you need to do, right? And that's a crucial question. Because what you do if you actually apply this is you evaluate the right-hand side for some finite n, right? That's what you can do. Right? You average the nth power of the partition function, n now being an integer, right? And doing this, you have to take all types of things. Do all types of things, right? You have to take maybe a zero temperature limit, a thermodynamic limit, do approximations, and then in the very end, you take this result that you evaluate for integer n, right? And analytically continue it takes the limit n to 0. And it's entirely unclear under what conditions these various limits that you're doing are actually commuting, right? And that's the reason why it sometimes doesn't work. You're exactly right. Okay, so we are not going to use this at all. I just wanted to point it out because it's a technique that's very commonly used for disordered systems, and in many cases it does work, but in many others it doesn't, right? Okay, so from now on, as I said, we are just looking at quench disorder. And one important idea that we discussed yesterday was the idea that phase transitions don't care much about details, right? They don't care much about microscopic details, but they care about symmetries and dimensionalities. So when one thing that's obvious in this context is to think about the symmetries of the disorder. So what symmetries of your system are preserved under the disorder, what are broken, and this will lead us to different classes of randomness that behave very differently. Go over there. we're going to classify the disorder by symmetries. And this is not supposed to be a complete and comprehensive classification. I just want to discuss a few commonly occurring cases. And let's start from an example. Let's again look at the toy model of a ferromagnet. So we start from a clean ferromagnet with a Hamiltonian minus J sum over Ij as Ij, right? So if you want, it could be a classical Ising model with some uniform interaction between the pairs of nearest neighbors. And now we want to make this disordered. So how could we make this disordered? Well, one way a theorist would think about this is to say, well, let's assume that there's some mechanism in our model produced by something over there, right? That actually leads to a random variation of the exchange interaction from point to point, right? And in the simplest case, we could then write it like that. Sum over Ij minus Jij as Isj, right? And let's assume the variations are weak, right? In particular, let me require that these Jij's are still all positive, right? So Jij are random, but all Jij are larger than 0, right? They're all ferromagnetic still. Okay, so what do you think will happen to the bulk phases, to the ferromagnetic paramagnetic phase if I do that?
We'll just lower the transition temperature a little bit.
I'm not sure about lower because I've not said what the values are. Before we go to the transition, let's simply talk about the bulk phases, right? In the clean case, we have two phases, right? If you assume this is all classical, then we have a paramagnetic phase at high temperatures and the ferromagnetic phase at sufficiently low temperatures, right? Provided we are on high enough dimensions and blah, blah, blah. Now, if I introduce this type of randomness, so I make some slight variations in the J's, keeps them all positive, what do you think what happens to the phases? What will happen at high temperatures?
There will be a Ising, maybe?
Still paramagnetic.
Nothing, right? The paramagnet will certainly be the same, right? And what about the ferromagnetic phase? Will also remain the same, right? If I just go sufficiently low, maybe in a naive version of this argument, below the smallest possible temperature set by J, right? Then it will all be ordered, right? So this type of disorder does leave the bulk phase is completely unchanged, right? So the only thing does, and now we come to your point, is that it will locally modify the tendency from one phase to the other. So if you want, this is the weakest kind of disorder you can think of, right? It does not at all touch the bulk phases qualitatively. They remain exactly the same. The only thing it does is locally change the tendency. Over here, it wants to be more ferromagnetic. Over there, it wants to be a little less ferromagnetic, right? So bulk phase is unchanged. But what changes is that locally the tendency towards ferromagnetism is stronger or weaker, right? Unchanged changes the local tendency towards one or the other phase. So it's clear this is a rather weak effect. in particular, if we're talking about symmetries, what about this? What about the symmetry? Is the symmetry changed here? The spin symmetry. Is it changed? The spatial symmetry is of course changed. It's not translation invariant anymore, but the symmetry in spin space is completely preserved, right? It's still fully up-down symmetric. So this does not break the spin symmetry. Okay, so what we have then is a type of randomness that locally changes the tendency towards the ordered phase, or in other words, just using somewhat sloppy language, we locally get different TCs. Over here, the interactions are a little stronger, so TC wants to be higher. Over here, the couplings are a little weaker, so TC wants to be a little lower, and so therefore one name that people use for this kind of disorder is random TC disorder. Right? So if you read somewhere random TC disorder, then that's what it means. Right? It's a disorder that does not change the biophases, but that locally shifts the tendency between the phases.
Question? Just
Yeah.
want to make sure. So here you're talking about classical spin, like Ising model, right? Not Heisenberg model.
Yeah, that's my example, right? But of course I can make exactly the same argument for any other model, right? Just put back the arrows on top of here, nothing changes.
But I mean, for Heisenberg model, the ground state is not. People are not sure about the ground state, right?
In 3 dimensions, people are certainly sure about the ground state.
Maybe
So I'm not sure if I'm taking what you just said too seriously, but if there's different local TCs, does that mean we now have a first order transition?
So that's why I said people call it random TC, and that's a very good point. I've not implied, and let me emphasize this, I've not implied that indeed over here we have a phase transition at some temperature, and over here we have a phase transition at another temperature. This will actually be a very important question in the very last lecture. Because what if that would happen, would imply that there's no sharp singularity anymore globally, right? And this is what I call a Smith phase transition, and while this occurs sometimes, it's not a generic case. So just because the couplings are random does not mean that there's a region here that undergoes a transition early, and another one here that does it late. Actually, generically, this will not happen, even so there are some interesting cases where it does, and there will be the topic on Monday. So this random TC has to be taken with a grain of salt, right? Because it does not imply that there are real different TCs in different parts. It just looks as if there were different TCs, right? Okay, so the question is, how do we build this into something like a Landau or Landau-Ginzburg-Wilson theory, right? So remember, yesterday we wrote down an Landau-Ginzburg-Wilson theory after we discussed that we need to actually generalize Landau's theory to include fluctuations by working with space-dependent order parameters. And of course now, let me just point it out in passing, for a quantum phase transition we would have to have order parameters that depend on both space and time, right? So then our Landau-Ginzburg-Wilson theory would look like this. What did we have? Tm squared plus mu m to the 4 plus the gradient m squared, and maybe all types of higher order terms, right? This was a clean Landau-Ginzburg-Wilson theory. How do you think we should build this type of disorder that we just discussed microscopically? Right? Microscopically, it could be brought about by some random modulation of the bond strength. So how could we build this into a Landau or Landau-Ginzburg-Wilson description? Where should the disorder go in this theory?
Gradients. Varied parameters.
Let's try to remember what the parameters stand for, right? So this was the term that punished spins to be anti-parallel, right? What was this? Distance from the transition, right? Now, if this TC is random, then it's clear that it must go here, right? Because locally, some point in space will have a smaller t, it's closer to the phase transition. Whereas another point will have a larger t, it's further away from the phase transition, right?
Should it also go into the gradient squared term?
This will actually, you can add it here, but it's a subleading term.
I see.
Yeah, so the leading term is here. As always, you can add anything in higher order and it will provide subleading corrections. But if you look at it from the question which is the most relevant one, it actually has to go here.
And that's because we are taking it near t equals 0.
Little t equals 0, yes, yeah, exactly. So then the modification would be that this uniform t, right, has to be replaced by some t naught plus some, let's say, delta t of x, right? And so let me add it. So that's the modification into the field theory. And now if you talk to high energy theorists, they will call this not the distance from critical point, but they will call this a mass term in their field theory. And therefore another name for the same type of disorder is called random mass disorder. It's the same thing. Modification is here, just using the field theory language. Random mass disorder. Okay, so that's one thing that could happen. And as you see here, the disorder actually couples to the quadratic term in the lambda theory, right? And it's nice because it means, as we discussed before, it does not break the spin up and down symmetry, right? But of course, you could also imagine disorder coupling to the linear term, right? So it means that that your orthogonal theory contains a term that looks like this, right? The b times m of x, which was the field term in the clean theory we wrote down yesterday, now goes to b of x times m of x. Yeah, this is a random function, right? So now you have randomness coupling linearly to the order particle. So what about the symmetries here? Is the spin symmetry preserved?
Locally, no.
Locally it's broken, right? Because locally, this m of x, of course, will want to be parallel to the local field. And so if the local field is positive, then the spins at that point want to be up. If the local field is negative, the spins want to be down. So locally the spin symmetry is broken. So that's a much stronger effect than we had over there. Symmetry. Whether or not it is preserved globally, of course, depends on the distribution of these B of x, right? And now I've not said what it is, I've just told you it's random, right? But if you choose a symmetric distribution, that's symmetric under the inversion beta minus b, right? Then the symmetry is still preserved globally in a statistical sense, even though it's clearly broken locally at every point. So this is a much stronger type of disorder because it locally breaks the symmetry, and because this form is suggestive, it looks like a magnetic field, right? People call it random field disorder. And if you were an experimentalist who could produce a random magnetic field on a microscopic scale, then you could actually test it out. Turns out that it's very hard. There are some tricks you can do. You certainly cannot do it with a simple lab equipment because microscopes are very small. So this have to be effective fields that you use for this. But the idea is very simple. So that's a random field, the random case of random field disorder. So if it breaks symmetry, let's see, whether or not it's broken globally, depends on distribution. And of course, these are just two examples, right? There's many other ways how this order could actually couple to your problem. Imagine you have a Heisenberg magnet. You could have a term in your Hamiltonian that actually adds some anisotropy, right? That locally prefers a certain direction, but this direction could be random, right? It could be that at this place the spins want to be up, over here they want to be this, and over here they want to be another 45 degrees, right? So this would be a different type of disorder, not covered by any of what we have written here. Random anisotropy disorder, or you could have even random signs in the interaction. You could have something like this, but not with a uniform sign, but with random signs. Then you get stronger disorder. Or you could have random phases in some quantum Hamiltonian. So there's many more possible cases. For these lectures, I want to stick to these two types. So in what's going to come, we will ask what either random mass disorder, which is, if you want, the weakest case, or random field disorder, which is rather strong, what these two types of disorder can do to a phase transition. Okay, so let's ask a few questions that can that seem to appear naturally if you add this order to a system undergoing a phase transition. Maybe we can collect these questions and then start addressing them, maybe the first one today. It's actually a hierarchy of questions, I would argue. Okay, so what questions would you ask? I give you a system that undergoes a phase transition, like the lithium polymer fluoride, for instance, that we looked at in the beginning of this class. And then I tell you I'm introducing this order into the system, which in this material you can actually do, has been done experimentally by replacing the holmium, which carries a spin, with a non-magnetic ion. So these are experiments that have been done. And so let's assume you do this, and so what are the questions you would want to ask if you're interested in the phase transition in this material, and you now put in this order?
Is there a new phase?
Is there a new phase, right? That's maybe the most basic question, right? Are the bulk phases changed, right? Right? And the way I wrote it, I mean to include the question of are there new phases, or some phases going away, things like that, right? Okay, so once you've established what phases there are, for instance, the answer could be that the bulk phases are the same, right? What other questions could you ask?
Critical behavior.
Okay, critical behavior, right? So let me put this at the very bottom. So certainly, you could ask, will the critical behavior of the phase transition change? So will the universality class change in the sense of that we discussed yesterday, right? But strictly before we can go there, we have to ask a number of other questions before.
Is the sharp
Right.
transition still correct?
And we still have to convince ourselves, is there still a phase transition, a sharp one, right? Maybe it's not sharp anymore. And as I said, we will look at examples of that type on Monday. But that's certainly the next question, I would say. If the phases haven't changed and I want to start thinking about transitions, the first question I would ask is, well, is there still a sharp singularity or not, right? Phase transition, and what I mean by this is, or is it smeared? Or is it smeared over a range of the control parameter, and we will make precise what I mean by this on Monday, okay? Okay, so let's assume it's still sharp. Now we are approaching your question, but you're not quite there.
Is it still the same order?
Exactly, right? So before we can talk about criticality, we need to decide, do we have a first order transition or a second order one, right? So that's the next question I would ask. So if you still have a sharp phase transition, it could still be first order or second order, so is the order the same as before, right? The order of the phase transition is changed. That's the third question. And now if we convince ourselves that we now do have a critical point, right? So let's assume the phase transition is actually continuous. Then we can ask, what about the critical behavior, right? So do we get the same exponents as before, which, using the language of yesterday, would imply that this order is just an unimportant detail that gets averaged out, right? Or do we get different critical exponents, which would then, using the language of yesterday, imply that this order is something relevant, just like symmetry or dimensionality, right? So these are the questions we actually want to address in the remaining 2 classes plus 10 minutes. Historically, actually, people work more like this, right? So the first real result was concerning the last question. And that's what we are looking at today, at now, in the remaining 10 minutes. And this will lead us to the famous Harris criterion. So that's 2b in my counting. For this ability of the clean critical point. Okay, so what is it about? Now let's assume we have a clean system that does undergo a continuous phase transition, so it has a critical point, and it has a certain set of critical exponents, and let's assume we know all that, right? And for example, imagine this, right? Imagine a classical Ising model if you want. And so the question that Harris asked is, if we now add a little bit of random TC disorder, meaning we make the J is random in our toy model here, but just a little bit, right? A small, narrow distribution. Will the critical behavior change? That was the question Harris asked. Will it change, or could it be that it stays the same, or maybe under what conditions does it stay the same? So let's consider a clean critical point. And we add weak random TC disorder. And the question is, will the clean critical point be stable or not?
When you say random TC disorder, is that the same thing as saying that after I add the disorder, it still expects the same symmetry as the clean order parameters?
Right. It's random TC disorder in the sense we just discussed it 15 minutes ago. So it's a disorder that does not break the symmetry of the order parameter, neither locally nor globally. It just changes the tendency between the two phases in a random fashion locally, right?
But I mean, for example, in principle, I could add it to the spite of the fourth term, or at the end of the fourth term.
Right.
That would still technically respect the symmetry.
Right.
It's less relevant than the.
Exactly. Yes.
But
And
it's
you
still fine.
And you could do this, and if you would do this actually at the technical level and carry out the renormalization group calculation, this would actually generate the term we wrote down there. Okay, and so Harris actually came up with a rather ingenious heuristic argument that answers this question. And to already tell you the answer is maybe. So, so how does it work? Harris said, let's take the sample and let's divide it into blocks. Okay, how large are these blocks? Well, let's make the blocks the size of the correlation links. So why do we want to do this? Well, we know correlation links means that all the spins inside of one block, they act as one, right? They are parallel, they are correlated. So all the spins inside one block, they act as one big superspin and fluctuate together, right? Okay, now because of the randomness, each block has a slightly different TC in the sense we discussed. Right? It's not a true TC, but it is a TC the system would have if the whole system would just look like the block, right? So there's a TC1 and a TC2 and a TC3 and a TC4 and so on. And they are slightly different, right? Because of the randomness in the couplings. Okay. And now here's a basic idea of Harris' argument. Harris says, well, what we need to do is we need to compare how much TC changes between the blocks. So that would be the variation of TC from block to block, right? We need to compare this with the overall distance from the phase transition. Meaning, if all the blocks are on the same side of the transition, we are safe. Then the transition will not change, right? That means small variations in TC compared to the overall distance from the critical point. However, if it's the other way around, if we have very broad variations of the local TCs, then what can happen is that some blocks are on one side of the phase transition, some other blocks on the other side of the phase transition, and then something new must happen. The system falls apart, it can certainly not be uniform. Okay, now let's work it out. It just takes 2 minutes, and then we are done for today. So we need to work out what are the variations of TC from block to block, right?
I have one question.
Yeah.
How do you define the blocks? If they have different TCs, the correlation length will be different, wouldn't it? Because
No.
they have a different distance from the...
There will be a little different, right? And that's actually a real concern if you want to go beyond this condition of just looking at the stability towards weak disorder. If you want to apply the argument to strong disorder systems, then this becomes a real problem. But for now, we have weak disorder, which means the correlation length is not that different from block to block, and this will only make small corrections. Okay? That's a very good point. Okay, so, well, what we need to know is, we need to know the variation of TC from block to block. So that's something like the variance of the TC distribution, right? So here I want to write this. Let's write this as delta TC, right? So that's supposed to be the variation between the blocks. So how will this change as I make the correlation length larger? How will it behave?
One over side is about d by 2.
Right. That's simply a central limit theorem argument, right? Because what happens is very easy to understand. Since these spins fluctuate together, what they see is the average value of the coupling strengths, right? They cannot distinguish something large here or here because they all fluctuate together. So what you need to do is you need to average the coupling strength over this volume, and then central limit theorem tells you that the fluctuations of this average go down like 1 over square root of the size, right? So that means this will go like psi to the minus d over 2, right? Psi to the minus d is the inverse volume and the square root from the central limit theorem. So the variations between the blocks get smaller as we make the blocks larger, right? That's intuitive, I think, right? But what we need to do is we need to compare this with the overall distance from the critical point, right? And so what's the relation between the overall distance from criticality and the correlation length?
1 over d.
Right? Remember, this is just simply the definition of mu, right? We wrote down yesterday that psi goes like e to the minus mu, right? And now I just rewrite this. So t is proportional to psi to the minus 1 over mu, right? And so now Harry's idea was to say that the clean critical point is stable